At the moment, machines are vastly less intelligent than people. However, we have predicted that they would eventually be super intelligent. How are we gonna get there from here? This video examines various potential technical directions. We examine networks and organizations, whole brain emulation, biological cognition, human-machine intelligence, and artificial intelligence. We rank them according to how likely they are to lead to superintelligence. The likelihood that the destination can be reached by at least one of the many paths grows. As superintelligence is any intelligence that performs significantly better cognitively than humans in almost all relevant fields, according to our provisional definition. The concept of superintelligence will be discussed in more detail in the following videos, when we will submit it to a kind of spectral analysis to separate several different potential forms of superintelligence. But for the time being, the general description that was just provided will do. Be aware that the definition is ambiguous regarding the superintelligence's implementation. And in terms of qualia, it's ambiguous as well, while it may be important for some issues, particularly ethical ones, whether superintelligence would have subjective conscious experience. Our main concern here is with the causes of superintelligence rather than with the metaphysics of mind. For example, the just programmed Deep Fritz is not a superintelligence on this definition, since Fritz is only smart within the narrow domain of chess. Certain kinds of domain-specific superintelligence could, however, be important. When referring to superintelligent performance limited to a particular domain, we will note the restriction explicitly. For example, an engineering superintelligence would be an intellect that vastly outperforms the best current human minds in the domain of engineering. Unless otherwise noted, we use a term to refer to systems that have a superhuman level of general intelligence. But how might we create superintelligence? Let us examine some possible paths together. Well, viewers of this video must not expect a blueprint for creating an artificial general intelligence. Of course, no such blueprint exists at this time. And even if I had had that blueprint, I wouldn't have discussed it in this video. And if you inquire as to why, I will address it in one of my upcoming videos. Well, we can, however, discern some general features of the kind of system that will be required. It now seems clear that the capacity to learn would be an integral feature of the core design of a system intended to attain general intelligence, not something to be tacked on later as an extension or an afterthought. The same holds for the ability to deal effectively with uncertainty and probabilistic information. Some faculty for extracting useful concepts from sensory data and internal states, and for leveraging acquired concepts into flexible combinatorial representations for using logical and intuitive reasoning, also likely belong among the core design features in a modern AI intended to attain general intelligence. For example, the early old-fashioned artificial intelligence systems did not, for the most part, focus on learning, uncertainty, or concept formation, perhaps because techniques for dealing with these dimensions were poorly developed at the time. This is not to say that the underlying ideas are all that novel. The idea of using learning as a means of bootstrapping as a simpler system to human-level intelligence can be traced back at least to Alan Turing's notion of a child machine, which he wrote about in 1950. Instead of trying to produce a program to simulate the adult mind, why not rather try to produce one which simulates the child? If this were then subjected to an appropriate course of education, one would obtain the adult brain. Turing envisaged an iterative process to develop such a child machine. We cannot expect to find a good child machine at the first attempt. One must experiment with teaching one such machine and see how well it learns. One can then try another and see if it's better or worse. There is an obvious connection between this process and evolution. One may hope, however, that this process will be more expeditious than evolution. The survival of the fittest is a slow method for measuring advantages. The experimenter, by the exercise of intelligence, should be able to speed it up. Equally important is the fact that he is not restricted to random mutations. If he can trace a cause for some weakness, he can probably think of the kind of mutation which we know that blind evolutionary process can produce human-level general intelligence since they have already done so at least once. Evolutionary processes with foresight, that is, genetic programs designed and guided by an intelligent human programmer, should be able to achieve a similar outcome with far greater efficiency. This observation has been used by some philosophers and scientists, including David Chalmers and Hans Moravec, to argue that human-level AI is not only theoretically possible, but feasible within this century. The idea is that we can estimate the relative capabilities of evolution and human engineering to produce intelligence, and find that human engineering is already vastly superior to evolution in some areas and is likely to become superior in the remaining areas before too long. The fact that evolution produced intelligence therefore indicates that human engineering will soon be able to do the same. Thus, Moravec wrote in 1967, the existence of several examples of intelligence designed under these constraints should give us great confidence that we can achieve the same in short order. The situation is analogous to the history of heavier-than-air flight, where birds, bats, and insects clearly demonstrated the possibility before our cultures mastered it. One needs to be cautious, so in what inferences one draws from this line of reasoning? It is true that evolution produced heavier-than-air flight, and that human engineers subsequently succeed in doing likewise, albeit by means of a very different mechanism. Other examples could also be adduced, such as sonar, magnetic navigation, chemical weapons, photoreceptors, and all kinds of mechanic and kinetic performance characteristics. However, one could equally point to areas where human engineers have thus far failed to match evolution in morphogenesis, self-repair, and immune defense. For example, human efforts lag far behind what nature has accomplished. Moravec's argument, therefore, cannot give us great confidence that we can achieve human-level artificial intelligence in short order. At best, the evolution of intelligent life places an upper bound on the intrinsic difficulty of designing intelligence. But this upper bound could be quite far above current human engineering capabilities. And another way of deploying an evolutionary argument for the feasibility of artificial intelligence is via the idea that we could, by running genetic algorithms on sufficiently fast computers, achieve results comparable to those of biological evolution. This version of the evolutionary argument thus proposes a specific method whereby intelligence could be produced. However, it is true that we will soon have computing power sufficient to recapitulate the relevant evolutionary processes that produce human intelligence. The answer depends on how much computing technology will advance over the next decades and on how much computing power will be required to run genetic algorithms with the same optimization power as the evolutionary process of natural selection that lies in our past. Very interesting part. The upshot is that the computational resource required to simply replicate the relevant evolutionary processes on Earth that produced human-level intelligence are severely out of reach and will remain so even if Moore's law will continue for a century. It's plausible, however, that compared with brute force replication of natural evolutionary process, vast efficiency gains are achievable by designing the search process to aim for intelligence. For example, using various obvious improvements over natural selection. Yet it's very hard to bound the magnitude of those attainable efficiency gains. We cannot even say whether they amount to 5 or 25 orders of magnitude. Absent further elaboration, therefore, evolutionary arguments are not able to meaningfully constrain our expectations of either the difficulty of building human-level machine intelligence or the timescales for such developments. There is a future complication with these kinds of evolutionary considerations, one that makes it hard to derive from them even a very loose upper bound on the difficulty of evolving intelligence. We must avoid the error of inferring from the fact that intelligent life evolved on Earth that the evolutionary processes involved had a reasonably high prior probability of producing intelligence. Such an inference is unsound because it fails to take account of observation selection effect that guarantees that all observers will find themselves as having originated on a planet where intelligent life arose, no matter how likely or unlikely it was for any given such planet to produce intelligence. Suppose, for instance, that in addition to the systematic effects of natural selection, it required an enormous amount of lucky coincidence to produce intelligent life, enough so that intelligent life evolves on only one planet out of every planet on which simple replicators arise. And in that case, when we run our genetic algorithm to try to replicate what natural evolution did, we might find that we must run some simulations before we find where all the elements come together in just the right way. This seems fully consistent with our observation that life did evolve here on Earth. Only by careful and somewhat intricate reasoning, by analyzing instances of convergent evolution of intelligence-related traits and engaging with the subtleties of observation selection theory, can be partially circumvented epistemological barrier. It's all sometimes difficult to sound this word. Well, another way of arguing for the feasibility of artificial intelligence is by pointing to the human brain and suggesting that we could use it as a template for a machine intelligence. One can distinguish different versions of this approach based on how closely they propose to imitate biological brain functions. At one extreme, that of very close imitation, we have the idea of whole brain emulation, which we will discuss in the next parts. At the other extreme are approaches that take their inspiration from the functioning of the brain, but do not attempt low-level imitation. Advances in neuroscience and cognitive psychology, which will be added by improvements in instrumentation, should eventually uncover the general principles of brain function. This knowledge could then guide AI efforts. We have already encountered neural networks as an example of brain-inspired AI technique. Hierarchical perceptual organization is another idea that has been transferred from brain science to machine learning. The study of reinforcement learning has been motivated, at least in part, by its role in psychological theories of animal cognition, and reinforcement learning techniques inspired by these theories are now widely used in artificial intelligence. More cases like this will surely accumulate in the future. Since there is a limited number, perhaps a very small number, very limited number of distinct fundamental mechanisms that operate in the brain, continuing incremental progress in brain science should eventually discover them all. And before this happens, though it is possible that a hybrid approach, combining some brain-inspired techniques with some purely artificial methods would cross the finishing line. And in that case, the resultant system need not be recognizably brain-like, even though some brain-derived insights were used in its development. The availability of the brain as template provides strong support for the claim that machine intelligence is ultimately feasible. This, however, doesn't enable us to predict when it will be achieved, because it's very hard to predict the future rate of discoveries in brain science. What we can say only is that the further into the future we look, the greater the likelihood that the secrets of the brain's functionality will have been decoded sufficiently to enable the creation of machine intelligence in this manner. Different people working toward machine intelligence hold very different views about how promising neuromorphic approaches are compared with approaches that aim for completely synthetic designs. The existence of birds demonstrated that heavier than air flight was physically possible and prompted efforts to build flying machines. Yet the first functioning airplanes didn't flap their wings. The jury is out on whether machine intelligence will be like flight, which humans achieved through an artificial mechanism, or like combustion, which we initially mastered by copying natural occurring fires. For example, Turing's idea of designing a program that acquires most of its content by learning rather than having it pre-programmed at the outset can apply equally to neuromorphic and synthetic approach to machine intelligence. Well, a variation on Turing's conception of a child machine is the idea of a seed AI, whereas a child machine, as Turing seems to have envisaged it, would have a relatively fixed architecture that simply develops its inherent potentialities by accumulating content. A seed AI would be a more sophisticated artificial intelligence capable of improving its own architecture. In the early stages of seed AI, such improvements might occur mainly through trial and error, information acquisition, or assistance from programmers. As its later stages, however, a seed AI should be able to understand its own working sufficiently to engineer new algorithms and computational structures to bootstrap its cognitive performance. And this needed understanding could result from the seed AI reaching of general intelligence across many domains, or just from crossing some threshold in a particularly relevant domain, such as computer science or mathematics. This brings us to another important concept, that recursive self-improvement. A successful seed AI will be able to iteratively enhance itself. An early version of the AI could design an improved version of itself, and the improved version, being smarter than the original, might be able to design an even smarter version of itself, and so forth. It continues like this. And under some conditions, such a process of recursive self-improvement might continue long enough to result in an intelligence explosion, an event in which, in a short period of time, a system's level of intelligence increases from a relatively modest endowment of cognitive capabilities to radical superintelligence. And I will return to this important possibility in my next videos, where the dynamics of such an event will be analyzed more closely. And note that this model suggests the possibility of surprises, like attempts to build artificial general intelligence might fail pretty much completely until the last missing critical component is put in place, at which point a seed AI might become capable of sustained recursive self-improvement. Well, and before I end this part, there is one more thing that I should emphasize. Which is that an artificial intelligence need not resemble a human mind. This is a very important part. AIs could be indeed, it is likely that most will be extremely alien. We should expect that they will have very different cognitive architectures than biological intelligences. And in their early stage of development, they will have very different profiles of cognitive strengths and weaknesses. Furthermore, the goal systems of AIs could diverge radically from those of human beings. There is no reason to expect a genetic AI to be motivated by love or hate or pride or other such common human sentiments and emotions. These complex adaptations would require deliberate, expensive effort to create in AIs. This is at once a big problem and a big opportunity at the same time. We will return to the issue of AI motivation in later videos, but it is so central to the argument in this video that it's worth bearing in mind throughout. Whole brain emulation. Well, this is my favorite part, which I always love to discuss because I hope and strongly believe we will have this someday in the near future, and this will change completely everything. Intelligent software would be created by scanning and carefully simulating the computational structure of a biological brain in whole brain emulation, which commonly referred to as uploading, meaning that uploading the whole brain to the digital. Thus, this strategy is a limited example of taking inspiration from nature, outright copying. The following task must be completed to reach entire brain emulation. First, a sufficiently thorough scan of a specific human brain is made. This might entail vitrifying the brain after death to stabilize it. The tissue might then be divided into slices by a machine and put into a different machine for scanning, possibly by a number of electron microscopes. At this point, several strains may be used to highlight various structural and chemical characteristics. Multiple scanning systems could operate in tandem to examine various brain slices at once. Secondly, the raw data from the scanners is fed to a computer for automated image processing to reconstruct a three-dimensional neural network that implemented cognition in the original brain. In practice, this step might proceed concurrently with the first step to reduce the amount of high-resolution image data stored in buffers. The resulting map is then combined with a library of neurocomputational models of different types of neurons and different neural elements. And then in the third stage, the neurocomputational structure resulting from the previous step is implemented on a sufficiently powerful computer. Interesting part. If completely successful, the result would be a digital reproduction of the original intellect. You see, with memory and personality intact, the emulated human mind now exists as software on a computer. Can you believe it? The mind can either inhabit a virtual reality or interface with the external world by means of robotic appendages. The world brain emulation path does not require that we figure out how human cognition works or how to program an artificial intelligence. It requires only that we understand the low-level functional characteristics of the basic computational elements of the brain. No fundamental conceptual or theoretical breakthrough is needed for world brain emulation to succeed. World brain emulation does, however, require some rather advanced enabling technologies. And there are three key prerequisites for scanning, which is a high throughput microscopy with sufficient resolution and detection of relevant properties. Second is translation, which is an automated image analysis to turn raw scanning data into an interpreted three-dimensional model of relevant neurocomputational elements. And the last one is simulation, which is a hardware powerful enough to implement the resultant computational structure. There is good reason to think that the requisite enabling technologies are attainable, so not in the near future. Reasonable computational models of many types of neuron and neuronal processes already exist. Image recognition software has been developed that can trace axons and dendrites through a stack of two-dimensional images. And there are imaging tools that provide the necessary resolution with the scanning tunneling microscope. And it's possible to see individual atoms, which is far higher resolution than needed. However, also present knowledge and capabilities suggest that there is no in-principle barrier to the development of the requisite enabling technologies. It is clear that a very great deal of incremental technical progress would be needed to bring human whole brain emulation within reach. For example, microscopy technology would need not just sufficient resolution, but also sufficient throughput. Using an atomic resolution scanning tunneling microscope to image the needed surface area would be far too slow to be practicable. It would be more plausible to use a lower resolution electron microscope, but this would require new methods for preparing and staining cortical tissue to make visible relevant details such as synaptic fine structure. A great expansion of neurocomputational libraries and major improvements in automated image processing and scan interpretation would also be needed. In general, whole brain emulation relies less on theoretical insight and more on technological capability than artificial intelligence. Just how much technology is required for whole brain emulation depends on the level of abstraction at which the brain is emulated. In this regard, there is a trade-off between insight and technology. In general, the worse our scanning equipment and the feebler our computers, the less we could rely on simulating low-level chemical and electropsychological brain processes. And the more theoretical understanding would be needed of the computational architecture that we are seeking to emulate in order to create more abstract representations of the relevant functionalities. And conversely, with sufficiently advanced scanning technology and abundant computing power, it might be possible to brute force an emulation even with a fairly limited understanding of the brain. In the unrealistic limiting case, we could imagine emulating a brain at the level of its elementary particles using the quantum mechanical Schrödinger equation. Then one could rely entirely on existing knowledge of physics and not at all on any biological model. This extreme case, however, would place utterly impracticable demands on computational power and data acquisition. A far more plausible level of emulation would be one that incorporates individual neurons and their connectivity matrix, along with some of the structure of their dendritic trees and maybe some state variables of individual synapses. Neurotransmitter molecules would not be simulated individually, but their fluctuating concentrations will be modeled in a coarse-grained manner. And to assess the feasibility of whole brain emulation, one must understand the criterion for success. The aim here is not to create a brain simulation so detailed and accurate that one could use it to predict exactly what would have happened in the original brain if it had been subjected to a particular sequence of stimuli. Instead, the aim is to capture enough of the computational and functional properties of the brain to enable the resultant emulation to perform intellectual work. And for this purpose, much of the messy biological detail of a real brain is irrelevant. A more elaborate analysis will distinguish between different levels of emulation success based on the extent to which the information processing functionality of the emulated brain has been preserved. For example, one could distinguish among a high-fidelity emulation that has the full set of knowledge, skills, capabilities, and values of the emulated brain. A distorted emulation whose dispositions are significantly non-human in some ways, but which is mostly able to do the same intellectual labor as the emulated brain. And a generic emulation that is somewhat like an infant lacking the skills or memories that had been acquired by the emulated adult brain, but with the capacity to learn most of what a normal human can learn. And while it appears ultimately feasible to produce a high-fidelity emulation, it seems quite likely that the first whole brain emulation that we will achieve, if we went down this path, would be of a lower grade. Before we will get things to work perfectly, we will probably get things to work imperfectly, as all in the processes, as it is also possible that a push toward emulation technology would lead to the creation of some kind of neuromorphic AI that would adapt some neurocomputational principles discovered during emulation efforts and hybridize them with synthetic methods, and that this would happen before the completion of a fully functional whole brain emulation. The possibility of such spillover into neuromorphic AI, as we will see in later videos, complicates the strategic assessment of the desirability of seeking to expedite emulation technology. There is one interesting question: how far we currently from achieving a human whole brain emulation? Let's look at it together. This is whole brain emulation roadmap. One recent assessment presented a technical roadmap, which is this, and concluded that the prerequisite capabilities might be available around mid-century, though with a large uncertainty interval. This figure depicts the major milestones in this roadmap. The apparent simplicity of the map may be deceptive, however, and we should be careful not to understate how much work remains to be done. No brain has yet been emulated. Consider the humble model organism Canor habditis elegans, which is a transparent roundworm about 1 millimeter in length with 302 neurons. The complete connectivity matrix of these neurons has been known since the mid-1980s, when it was laboriously mapped out by means of slicing, electron microscopy, and hand labeling of specimens. But knowing merely which neurons are connected with which is not enough. To create a brain emulation, one would also need to know which synapses are excitatory and which are inhibitory, the strengths of the connections and various dynamical properties of axons, synapses, and dendritic trees. This information is not yet available even for the small nervous system of C. elegans. Success at emulating a tiny brain such as that of C. elegans would give us a better view of what it would take to emulate larger brains. And at some point in the technology development process, once techniques are available for automatically emulating small quantities of brain tissue, the problem reduces to one of scaling. Notice the ladder at the right side of this figure. This ascending series of boxes represents a final sequence of advances which can commence after preliminary hurdles have been cleared. The stages in the sequence correspond to whole brain emulations of successively more neurologically sophisticated model organisms. For example, C. elegans to honeybee to mouse to rhesus monkey to human. Because the gaps between these rungs, at least after the first step, are most quantitative in nature and due mainly to the difference in size of the brains to be emulated, they should be tractable through a relatively straightforward scale-up of scanning and simulation capacity. Once we start ascending this final ladder, the eventual attainment of human whole-brain emulation becomes more clearly foreseeable. And we can thus expect to get some advance warning before arrival at human-level machine intelligence along the whole-brain emulation path, at least if the last among the requisite enabling technologies to reach sufficient maturity is either high throughput scanning or the computational power needed for real-time simulation. Well, and if, however, the last enabling technology to fall into place is neurocomputational modeling, then the transition from unimpressive prototypes to a working human emulation could be more abrupt. One could imagine a scenario in which, despite abundant scanning data and fast computers, it's proving difficult to get our neuronal models to work right. When finally the last glitch is ironed out, what was previously a completely dysfunctional system, analogous perhaps to unconscious brain undergoing a grand mal seizure, might snap into a coherent wakeful state. And in this case, the key advance would not be heralded by a series of functioning animal emulations of increasing magnitude. Even for those paying attention, it might be difficult to tell in advance of success just how many flaws remained in the neurocomputational models at any point and how long it would take to fix them, even up to the eve of the critical breakthrough. Once a human whole-brain emulation has been achieved, further potentially explosive developments would take place, but I postpone the discussion of this until next parts of my videos. Surprise scenarios, of course, always can happen. And surprise scenarios are those imaginable for brain emulation, even if all the relevant research were conducted in the open. Nevertheless, compared with the AI path to machine intelligence, whole brain emulation is more likely to preceded by clear omens since it relies more on concrete observable technologies and is not wholly based on theoretical insight. We can also say that with greater confidence than for the AI path, that the emulation path will not succeed in the near future, at least within the next 15 years, say. Because we know that several challenging precursor technologies have not yet been developed. By contrast, it seems likely that somebody could, in principle, sit down and code a seed AI on an ordinary present-day personal computer. And it will be ridiculous, because such things must take time, as all the technology we have did. And it's conceivable, so unlikely that somebody somewhere will get the right insight for how to do this in the near future.